Hello everyone. In this session, let me continue the theorems on measurable set. Remember, I am telling you again and again, measurable set is same as Leberque measurable set. Leberque measurable set, and outer measure is same as Leberque outer measure. But the same theorems will be there in measurable set as well in outer measure of a given set, or Leberque outer measure. So while reading the statement, go through the statement carefully and then start writing the proof. Now I am talking about Leberque measurable set or a measurable set. Now we have it is already clearly explained in a previous session. Now we have a theorem on measurable set or Leberque measurable set. The collection mu or m, whatever may be the it is a representation. I can say this as a collection m. Okay, collection m of all measurable sets in R is an algebra of set in R. The key point is that if mu is a set of all measurable set, or as I can say it is a collection of all measurable set, then we have to prove this mu or m as algebra. So the very first video you can see what you mean by algebra of a set. It should satisfy two conditions. First one is it should be closed under its complementation, that is complement of a set should also belong, and second condition is that it should be closed under finite union. So if these two conditions satisfies, we can say given set is a algebra. Now we have to take one set which contains all the measurable set, or we have to take one collection mu which contains all the measurable set, and we have to prove that is an algebra of a set. Now let me do that. Let me take a collection of sets mu is say E, which is subset of R, such that E is a collection of measurable set. So what I have taken is mu as a collection of all measurable set. Now suppose if E is measurable, I have already chosen that E is measurable. So as per the definition of measurable set, if E is measurable, then for any set A which is subset of R, you just revise the definition of measurable set. If E is said to be measurable, then there exists any set A which is subset of R such that measure of A is equal to measure of A intersection E plus measure of A intersection its complement. You have to remember this definition. If a given set is measurable, then there exists another set which is subset of a relation R such that it should satisfy this condition. If E is measurable, then you have to put E here and E complement here, intersection with the subset. You have to remember this condition. Fine. Now what I am going to do is I am going to replace E with E complement. See, all this simplification will not be there in the notes. You just go through the video, then you will clearly understand the steps mentioned in the notes. Now what I am going to do is replacing E with E complement. Then you will get M star A intersection E complement plus M star A intersection E complement. I am going to replace it with again E complement. Fine. So let me write E complement whole complement. Clear? Now you can clearly see that since I have chosen E is measurable, so if E is measurable as per the definition, E should be there and its complement should be there. Now look at the definition of this statement. In the sense, what I have done is I have replaced E with E complement. So in place of E, I have E complement. See here, E complement whole complement is there. So in place of E, E complement is there. Meaning is if E is measurable, then this condition satisfy. So if this condition satisfy, in place of E, what we have? E complement. So clearly I can say E complement is also measurable. Clear? In the sense, E complement belongs to the collection of measurable set. This is very important. I'm repeating this first condition once again. We have to prove this collection mu is an algebra. First condition, we have to prove it is closed under complement. Second condition, we have to prove it is closed under its union. Now I have already proved the first condition. It is complementation. See here, what I have chosen is E is a measurable set as per the definition of assumed collection of measurable set mu. Since E is measurable as per the definition of measurable set, then there exists a subset of R. This condition is satisfied. Now what I have did is replacing E with E complement. So wherever E is there, I have obtained E complement. Meaning is this condition is also satisfying. In the sense E complement is also measurable. E complement is measurable in the sense mu is collection of all measurable sets, right? So E complement is also belongs to mu. So I can say mu is closed under complementation. Closed under complementation. Why? Because see here, I have chosen E belongs to a mu, right? E is in the set mu. What I have proved is E complement is also in the same set. So E is there and its complement is also there. So I can clearly write it is closed under complementation. Now the very important concept is second one I have to prove, right? First one I have already proved. Second one is I have to prove it is closed under its union. Fine. Now let me take any two open sets. Measurable sets from a collection mu. Let me take E1 and E2 belongs to mu. That is U1 and E2 are measurable sets. All the definition will be clearly given in the notes, but I am not writing all the definition. I am manually explaining it. So E1 and E2 are two measurable sets in the collection mu. Then we have to prove that. Let me take E1 intersection. I have already told you that if E1 and E2 are in M, in the sense a collection of measurable set, then their intersection will also be in mu. I'll give you the proof of this in the next video, but remember, if any two sets are measurable, then their intersection is also measurable as per the property of measurable set. This is already said in a previous video. You have to just go through the video. Their intersection is also mu. Mu is another than a collection of measurable set, right? Since E1 is measurable, why? Because E1 belongs to mu. Mu is collection of measurable set. So as per the definition of measurability, I can say there exists a subset of R such that M star of A is equal to M star of A intersection, whatever is there, you just write it. E1 plus M star of its complement. Fine. Let me take that as equation 1. Clearly E2 is also belongs to mu. So by the definition, E2 is measurable, right? So I have already chosen A. Let me take another set B, which is subset of R. Then by the definition I can say M star of B is equal to M star of B intersection this set E2 plus M star of B intersection this set's complement. In the sense E2 complement I can write. Let me take this as equation 2. Now what I am going to take is, let me replace B with A intersection E1 complement. Fine. I am just replacing B with A intersection E1 complement. So I'll get M star of A intersection E1 complement is equal to M star of A intersection E1 complement intersection E2 plus M star of A intersection E1 complement intersection E2 complement. Let me take this as equation 3. What I have done is replacing B with A intersection E1 complement. That's all. So when you do this, now let me keep this as equation 3. Now we can write any set E1 intersection with E2 as E1 union E2 minus E1. Shall we write like this? I'll give you simple counter example. See, these are all properties of sets. So for each and every statement I cannot convince you, I cannot give you counter example. But when I write, you have to, if you are finding difficulty with that, you have to take one counter example and you can verify this. See here, right now I am just convincing you this statement, how I have written. Suppose let me take a set E1 as like 1, 2, 3, 4, 5. Fine. And let me choose E2 with an element 2, 3, 4. Now, if you are going to calculate E1 complement will be when you are going to subtract E2 from E1. So it is basics and it will be there in 10th standard textbook. You should go through that if you are finding difficulty with this. So finding complement will be subtracting this set from the first set. So that will give us 1, 5. Now let me calculate E1 union E2. that is LHS value I'm calculating. So E1 union E2 will be 1, 2, 3, 4, 5. Clear? Now E2 intersection E1 complement, I'm calculating RHS value. E2 intersection E1 complement. E2 is here. Intersection with E1 complement is here. So you have to take intersection of these two. Do we have any common elements in between these two? We don't have. So it is null set. Clear? Now I have already calculated the LHS value. I have taken this as 1. Now I am going to calculate RHS value. RHS is E1 union E2 intersection E1 complement. So I have to take E2 intersection E1 complement. This value union with E1 value. So null set union with this value will be first value you will get. Right? So now look at the equations 1 and 2. I can write E1 union E2 will be equal to E1 union E2 intersection E1 complement. That is what I have written. See here. Clear? See, these are all properties of sets. Not only in this theorem, I am going to use so many properties of sets in almost all theorems of measure and integration. Please go through the properties of sets once again. It will be there in real analysis basics. Madam has already told you, I think so. So E1 union E2 intersection E1 complement will be equal to E1 union E2. So this is how it comes. I just given a counter example. Now what I'm going to take is, let me continue the theorem. Just this is only for your understanding. I have given a counter example that how I can write E1 union E2 as E1 union E2 intersection E1 complement. For this statement I have given this counter example. Fine. Now let me continue with the theorem. I am going to take intersection with A on both sides. So A intersection E1 union E2, which is equal to A intersection E1 union E2 intersection E1 complement. Fine. Now again let me split this term A intersection E1 with the first term union A intersection with the second term E2 intersection E1 complement. I have splitted this intersection term. That's all. I have not done anything else. Now I can remove this bracket, or else let me keep as it is. I will write LHS part also. Union U2. Now let me rewrite this statement once again. So I'll get A intersection E1 union E2 will be equal to A intersection E1 union A intersection. I'll just replace this E1 complement intersection E2 complement. E2, one and the same. Like A intersection B, I can write this as B intersection A. So that is how I have written. See here, LHS as it is I have written. First term as it is. Second term what I did is E2 intersection E1 complement. I have written that as E1 complement intersection E2. One and the same. Now what I'm going to do is, let me take measure on both sides. So what you're going to get, measure of A intersection E1 union E2 will be equal to M star of A intersection E1 union A intersection E1 complement intersection E2. Just I have applied a measure on both sides. Let me take this as equation 4. Remember, all these steps are not clearly mentioned in the notes. I am just explaining for your reference. Fine. Now look here, what I have taken is E1 union E2. Suppose if I am going to take E1 union E2 whole complement, you will get E1 union E2 intersection E1 complement whole complement. So the minute when you are going to split it, you will get E1 complement intersection E2 intersection E1 complement whole complement. Just I have applied the De Morgan's law. Now let me split this once again, so that you will get intersection E2 complement will become E2 whole complement. I am going to split, intersection will become E1. So here E1 complement whole complement you are going to get. Again I can write that as E1. Remember, E1 complement whole complement I can write as E1. Something like A complement whole complement will be equal to A. Fine. Now this is what I have done. E1, this is for complement of a set. So same procedure I am going to take now. Now let me take intersection on both sides. E2 whole complement is equal to A intersection with E1 complement intersection E2 complement union E1. Now let me take measure on both sides, so that M star of A intersection E1 union E2 whole complement is equal to M star of A intersection E1 complement intersection E2 complement union E1. Just I have applied the measure on both sides. Now let me take this as equation 5. Fine. Now let me add equation 4 and 5. So adding 4 and 5 will give us M star. Let me add LHS on both sides. A intersection E1 union E2 plus this term I have to add M star of A intersection E1 union E2 whole complement will be equal to, what I can write is what you have here in equation 4 is M star of A intersection E1 union A intersection E1 complement intersection E2 plus M star of A intersection this term E1 complement intersection E2 complement union E1. Just I have added LHS side of both the equation 4 and 5 and RHS side of equation 4 and 5 and I have written the same. Fine. Hope so it is clear for you. Now I am going to split this measure for the term, so I can rewrite this as M star of A intersection E1 plus, remember when you are going to split the measure, equal symbol will become less than or equal to as per the property. So when you are going to take measure, splitting the measure term, equal sign become less than or equal to. So I can write M star of A intersection E1 plus M star of A intersection E1 complement intersection E2 plus this term M star of A intersection. See here, this term let me rewrite once again. E1 complement I'll write as it is, intersection I'll write as it is. See here, what I have done is I have splitted the measure. So the minute when you split the measure, equal sign become less than or equal to. This term I have written as it is. Now since I am splitting the measure, union will become plus as per the monotonic property and I have written this statement as it is. Now what I am going to do is, let me keep this term as it is, this term also as it is. Now I am going to simplify these two terms. Remember when you are going to take union, we are going to take you will get first term itself. And let me explain that property also so that you will remember easily. And one second. See here, suppose if you are going to get, remember these properties of set. You can take the counter example and if you want you can check. See here, A union B. If you are going to apply union, you will get first set only. If you are going to get intersection, you are going to get second set. These are very important property. Suppose let me take A with elements 1, 2, 3. And B with elements say 2. So let me take intersection. A intersection B will be 2. That is what the set B is. Fine. Let me take A union B. A union B will be 1, 2, 3. If you have common element, then only this property holds good. That is, meaning is these two sets should not be disjoint sets. So A union B will be 1, 2, 3. This is what the set A is. So remember, when you have union, rest of the theorems I am going to write it strictly. I am not going to give counter example again and again. Remember, when you have union, you can directly write first set. When you have intersection, you can directly write second set. So that is how I can write here. Since I have union, I can directly write the first set. This is what the intersection is. E1 complement intersection I have written as it is. I have applied the property for these two terms. So since you have union, I can write the first term as it is. Clear? Now what I have obtained is, let me write LHS part once again. That is M star of A intersection E1 union E2 is less than or equal to, I have this expression. Fine. Now look at the first equation. What I have is M star of A is equal to M star of A intersection E1 plus M star of A union, M star of A intersection E1 complement. Or else before using equation 1, let me make use of equation 3 in order to simplify this equation. See, in equation 3, look at equation 3. These two terms can be written as M star of A intersection E1 complement. See here, I have these two terms here. Find M star of A intersection E1 complement intersection E2, M star of A intersection E1 complement intersection E2 complement. Now, using equation 3, above equation can be written as M star of A intersection E1 union E2 can be less than or equal to M star of A intersection E1 plus this can be written by using equation 3 as M star of A intersection E1 complement. Fine. We can write like this. Now look at the equation 1. equation 1 we can make use now. See here, m star of a intersection e1 plus m star of a intersection e1 complement. These two terms can be written as m star of a. So I can replace this with m star of a. So from using 1 in above equation, all these steps are clearly not mentioned. Remember, when you look this video, when you watch this video, then only you can revise the steps. So using equation 1, I can replace this with m star of a. So let me write LHS as it is. So I can replace this with m star of a. Clear? Now, or else I can write this statement as just reversing this inequality. Oh, I'm sorry, I missed this term here. In LHS, one more term I have m star of a intersection e1 union e2 whole complement. Now, just by reversing this inequality, something like if a less than b, I can write b greater than a. In the same way I am writing this, since I have less than or equal to, I can write greater than or equal to m star of a intersection e1 union e2 plus m star a intersection e1 union e2 complement. I can write. Fine. Remember this statement. Now, as per the definition, what we have to prove is it is closed under finite union, right? In the sense, in place of E, see, as per the definition of measurability property, in place of E, I should have E1 union E2. Then only we can say it is measurable. Fine. So, here, look at the statement. We have already proved that greater than or equal to inequality and less than or equal to inequality is also true. It is always true for all the expression, and it is already told in the properties of measure of a Leberque measure of a given set. So I can replace E with E1 union E2. As per the definition, when E is measurable, this property holds good. You just compare this equation with this. So in place of E, what I have obtained is E1 union E2. This implies E1 union E2 is measurable. In the sense, E1 union E2 is also belongs to a collection of measurable set. First condition, I have proved it is closed under complementation. Second condition, I have proved that it is closed under finite union. Theorem is somewhat big or lengthy, but anyhow, you just go through the statements, and a counter example is also given for each and every statement. I have tried my level better to convince you, but please go through once so that you will understand well. So I have proved both the condition, hence it is a algebra. Algebra in the sense I have to prove both the condition, right? First one is complementation and the second one is union, countable union. So complement also belongs to the collection and union also belongs to the given collection mu of a measurable set. Therefore mu is an algebra of set. So I will send you the notes, you just copy it. And corollary of the same statement, for this statement you have a corollary, and that will be proved in next session. Thank you.